Okay, good morning. So this organizing committee, I think, on one hand knew what they were doing and not letting us introduce ourselves, because they probably knew that we would take a lot more than that allotted time to do it. So you've all gotten a sense of the range of expertise of this group. I think the challenge that we've faced since invited to sit on this panel, and we've only had maybe a month or two longer than you have this morning to think about a 35-year time frame shift, is that is way outside of the time frame in which I think any of us strategically plan academically, scientifically, and Noubar can speak in terms of sort of business development and entrepreneurial strategic planning. It's a long way out. So in that sense, I think we're all challenged to try to think, well, can we kind of break the conversation down and think in decade-long increments, or what would be accomplished in 17 and a half years, and then double that out to 35. As I've thought about this discussion this morning, I guess one reflection I had is that I've been in the oncology field now just a hair less than 20 years. And I'm largely working on the same problems. Things that I really did think were going to evaporate as impediments are still there. And some of those are scientific, some of those are kind of cultural in the system, both academic and private sector, maybe even a little bit regulatory, although I have to say in oncology we have had the benefit of a very innovative regulatory environment, so we obviously can reflect on that domain as well today, but all of us are trying to advance science and medicine really with the broadest perspective of all the constituents in this ecosystem, and I think that's unlike the panels that we are following now and Calum's panel late yesterday, which are taking an AI focus. I think our task today is to think aside from that, science attempts to translate science to medicine. How can we imagine the idea of increasing the cycle time so that initial discoveries, initial experiments lead to attempts at human innovation, quicker readout times? How can we more rapidly learn? I'll finish with my kind of brief kind of perspective going into this discussion, that when I say that I'm working on a lot of the same problems that kind of envisioned 20 years ago might have already been solved, the simple-minded talking point that I had when I was looking at an oncology career and trying to pitch myself as someone who might be useful in that field is that the HIV revolution had just begun, in that AZT was at the time being followed by doublet inhibitor therapy, and then triple agent therapy came pretty quickly behind that. But the cycle time in terms of learning about resistance to AZT and the ability to then develop rational combination therapy and really blow the door open in that disease, I thought had its cancer paralog, admitting that cancer is more than one disease. And the problem that we have faced is that our repertoire of drugs is small. Our ability to combine agents and to start to explore combination space is really constrained, and that remains true in 2019. So thinking to 2054, I think the luxury of that time frame is that we figure that all of these shackles are going to fall away some way, somehow. But the job of this group is to be thinking about, kind of what are those most important paradigm-changing, venues for research that we envision, where there's, some, impediment that needs to be knocked out or some new capacity created. So let's jump in. Noubar, I thought maybe you could help, start us from the high-level framing. None of us are hospital administrators, so we're not thinking so much about how we engineer, hospitals going forward, but the whole health ecosystem in 35 years. What are the kind of framing principles of that? What are the determinants of the health system? Who are the constituents that are really leading the this whole domain of disease diagnosis and management differently than how we see things today?
Boy, I thought if I'm sitting all the way here, I can go last, no. But there that went. So much for scenario planning. So look, my perspectives are that of a life science entrepreneur and innovator. I don't really deal with the healthcare delivery and the healthcare system in general, and I'm quite happy about that, other than as a consumer once in a while, just because I think that is a completely different world, but they're connected. So, but I will restrict my comments to kind of the process of innovation. I think going into this, thinking ahead 35 years, on the one hand, it's a daunting task to try to predict. It's also useless in some level. But I would say that the one thing I would say is part of the reason it's hard to predict is because I think that much of what innovation is simply a Darwinian evolution process. And any more than we could predict forward what an evolving species will become without knowing each of the sequential competitive situations it will be in order to survive and gain advantage, I think similarly, this is a completely emergent process. And so while each of us can have a bet as to which of the current idea species will survive and will flourish, I think it has so much to do with the iterative nature of it that, on the one hand, I think this is a difficult thing to do. On the other hand, if you assume that the doubling time is so slow, which it is in our industry, that once every 10 or 15 years something new happens, then we're a couple of generations away and we can start thinking that maybe what exists 10, 15 years from now will be already the determinant of that future. So having said all of that, I kind of came at this a little bit differently, which is that I think that for me, the single biggest opportunity, if we roll the clock forward far enough, that the current forces that benefit from the current system have less of a say in what's possible. 35 years is an interesting time frame for that. I would like to imagine a complete reframing of the healthcare challenge to perhaps thinking about it the way we think about security. And I saw on the calendar, on the agenda today, Ash Carter will be speaking later. And I've for the last 25, 30 years, been working on early detection, diagnosis, prevention, and can't find a business model that sustainably rewards that. And I keep thinking that surely it's better for patients to be able to have that as a service, but it's just not financially viable. And I would say, to keep my comments short then, I think it has to do with the way we framed it. We don't have a Department of Peace in this country. We have a Department of Defense, because we framed the problem as that of a threat to our security. I think we could think about all of the diseases, whether it's neurological that we're here about, or cardiovascular, or cancer, or infectious, as a series of security challenges to what we're born with, which is an onboard capacity to be able to secure our health, an immune system, various other kind of well-evolved systems, which deteriorate over time. And if we start thinking about it from a security standpoint, such that drugs or surgery are the last line of defense, not the first thing that we do, I think that the future will look different, and prevention and detection will be the most profitable things to do, just like they are in the world of human defense. Imagine if we said, let's make sure the enemy really gets in, it's at our doorstep, and then we can blow them up. We don't do that. We keep them away from our shores, we keep them neutralized, we have intelligence to detect where they're coming from. All things that otherwise are known to us as detection, early detection, liquid biopsies, etc. So in my imaginary world, a single reframing of the problem, by the way, would do away with insurance, because private, rich people might get private security, but most of us rely on a deal we've made with a government. Right. That's not the case in health. Yeah. So I'll stop with that.
No, that's good. So I think that nicely sets up Calum attempting to solve the problem. How do you frame putting sensors in the population to detect disease emergence, understand what's modifying disease, just kind of create the sampling space to try to actually realize that goal.
So I look at it actually fairly similar to Noubar in a slightly different way. I think one of the things that we tend to do is we, in medicine, have sort of put a lot of the faith in the information that we've always put our faith in. And what we need to do is, I think, open up the information that we need to collect in order to inform our wellness, our health, the transitions to disease. And I think that means that we don't actually determine it ourselves. I think there are lots of examples where simple metrics like just how you live your life are actually a much better predictor of your risk of any downstream disease than any of the features that a physician or a biomedical enterprise would measure. There are lots of great examples of this, 6 randomized trials of taking ICU level telemetry and moving it into the home, and you're not even able to influence 30-day readmission rate, but yet telephone chatter predicts readmission rate if you know that you already have heart failure. So I think we just need to change the scope and scale of the information that we consider valuable. I think we're vastly underdetermined in medicine, and almost everything, whether it's a new sensor for let's say, interstitial fluid in your lung, or just a new sensor for how you're living your life in a collective social environment. Those are all, I think, very powerful tools that if leveraged properly can inform the future. And what we're really looking for, again, to Noubar's point, is to change the culture, is to engage and make patients active, have the system be surveilling rather than expectant, and to move to continuous rather than episodic monitoring and intervention. And I think if we start to take those attitudes, you begin to see barriers breaking down, because in reality, the information we're collecting in behavioral health informs our risk of cancer, our risk of cardiovascular disease, and vice versa. So we just need to retrain the system. Much of what we, I believe, see as bugs are actually features that we've put in there as a result of cultural entrainment. We teach ourselves, we teach our patients to behave in particular ways, and we need to change that culture quite dramatically if medicine is really going to advance. I think the final sort of statement in that vein is, I think it's absolutely ludicrous, and you've heard some people today talk about it, that research and clinical care are separate businesses. That there's absolutely no way that we can potentially dissect any of the complexity of human biology unless everybody who's willing and able is contributing to it. So that every clinical care transaction, every wellness interaction should be informing the mass of data that we are then assembling around understanding and breaking down the barriers between biological science. And if we're not doing that ab initio, if care is not actually intrinsically part of what we do as we're trying to learn about biology, then we're going to miss the boat completely.
Yeah, I think we're right at this tipping point, at least in dialogue in the field, with the idea that when it comes to therapeutics, that therapies stay in an incubator space in clinical trials, not in the quote unquote real world, and then they're unleashed in the real world, and God knows what happens thereafter. Occasional severe adverse events are reported, but that's about it. But the idea of not just blurring that line, but eliminating that line and having the entire, from first patient treated to millionth patient exposed, having that be the entire training set, and having drugs basically unleashed into that training set in gradual ways.
Iteratively closing the loop.
Yeah,
the learning health system that Greg talked about in the opening, that's exactly where we should be headed, and we won't get to 2054 without it, I hope.
Yeah. So Rudy, I think another maybe intuition that the organizing committee had in putting this panel together and targeting 2054 is that life expectancy continues to increase. It becomes then extremely likely, if people are living to 120, that they're going to get cancer. They're almost certainly going to get neurodegenerative disease out in those time frames as well. But increasing the cycle time in terms of making progress around neurodegenerative disease, it strikes me as an oncologist, throwing grenades over into the neurodegenerative disease space, is that the sensing technology has been a limiting factor. So in other words, knowing that disease has initiated, knowing that it's evolving, and then being able to try to monitor the effects of currently investigational drugs has been a rate-limiting step, and has made it so that the cycle time in terms of trying to translate, the recognition that amyloid deposition is a problem, but then trying to frame that as a endpoint, has been an example of a slow cycle time. So how do you envision sort of tightening that cycle time in neurodegenerative disease?
I would echo the thoughts of Noubar and Calum that the answer will be a mantra of early prediction, meaning knowing your family history and your genetics in terms of what's the risk you face just coming into this world for a neurodegenerative disease like Alzheimer's. And then that will guide at what point you do early detection. So we tell people, if you're in a family with Alzheimer's disease, look at the earliest age of onset, and a first-degree relative, subtract 20 years, and that's when you want to start looking for problems, because that's when you want to start treating, and that's early intervention. And we take for granted that unlike cancer, diabetes, and heart disease, we wait until the brain degenerates to the point that you have dementia before we treat. Alzheimer's disease. If we did this in cancer or heart disease, diabetes, people wouldn't live. But we think it's okay to do this for neuropsych. So we have to turn that back. And we see one failure after another, most recently another amyloid failure with aducanumab from Biogen, because we're simply treating that pathology too late. It's like someone having congestive heart failure and Calum says, that's okay, just take Lipitor. You wanted to do that 10 years ago. And we have to get into that same frame of thinking for brain diseases that involve neurodegeneration and detecting that pathology 10, 15 years before symptoms by imaging or blood tests, and then you start treating at that point.
But does that also mean taking a risk on biomarkers? And what I mean by that is before having fully validated biomarkers that absolutely cleanly relate to a 20-year outcome, taking a little bit of a leap and saying, okay, well, we have some human evidence, we have some model evidence that supports this is probably an intermediate biomarker. Let's think about targeting that as our endpoint. Again, a provisional commitment in the field, regulators buying in as well, as an attempt to try to increase the cycle time. Is that
yeah,
part of
I
your
think,
view?
the controversy around amyloid, for example, in Alzheimer's comes from two main things. One is that in mice, you put in the early onset Alzheimer's genes that we ended up discovered, and you get plaques, but you don't get the rest of the disease. Well, it's because mice don't make tangles. We can explain that now. If you use a brain organoid of human neurons, you see amyloid directly causes tangles. The genetics shows that amyloid is the trigger of this disease. All of these genes have in common deposition of amyloid. So I think at that point, it's a safe bet. There are many ways to get amyloid seeded or deposited in the brain, but hitting that early on stops the trigger. So I like to say, the plaques are like the match, the tangles are like the brush fires. But it's the neuroinflammation, it's the forest fire. We're taking patients where there's a forest fire blazing and thinking we can just blow out the match. And then we wonder why the trial doesn't work. But I think I think in 2054, they'll look back and not just be surprised, but appalled that we waited for people's brains to degenerate before we treated them. It will seem pretty silly by then.
So Marcela, being one who's focused particularly on sort of intracellular drug targeting, and recognizing that our scale of progress or pace of progress in getting from, a few dozen, some dozens of small molecule inhibitors of intracellular targets has really been quite gradual when you consider 20,000 genes and 15,000 of those anyway being protein encoding and post-translational modifications. There's a broad repertoire of target space that we are not addressing yet. I'm hopeful that covalent inhibitors will broaden that set a bit. I'm hopeful that chaperone drug delivery approaches will increase the repertoire a bit. But thinking outside of what we can accomplish in terms of intracellular manipulations, this is where your career has, I think, toggled. So between monoclonal antibodies, payload delivering monoclonal antibodies, now putting a cell on the back end of that as a payload. I guess I've been thinking about your work and your field as being, in this 2054 frame, this quantum leap from bone marrow transplant where we didn't really know what we were given back, right? Take it out, rinse it off, and give it back, hope for the best. Or even adoptive T-cell therapy where you take infiltrating lymphocytes in a patient's tumor and figure, well, there's probably some good guys in there. Let's grow them up and give them back. How do you see the natural evolution going forward in cell therapy? In cancer to start with, because that's your swim lane. But I guess I also want to kind of conceive of when you have cellular therapies that aren't just destroyers of targets, but modulators of targets, then maybe we can be thinking about cardiovascular and even neurologic disease applications. So if you could sort of tee us up in terms of how do we think about cells evolving from neutron bombs to smart tools?
Yeah, thanks, Keith. So I've been so lucky to participate in some of the evolution around cell therapies. I think just in the last 2 years is the first time that we've really seen cells be used as therapeutic agents. And if you think about the complexity of giving a cell compared to a small molecule where changing a hydroxyl group can make a big difference, you think about all the things that you can manipulate in a cell. It's proteome, it's RNA, it's genome, it's payloads. It's just orders of magnitude more complex, which I think really brings together a lot of different fields in biology as well, because we can take what we learned from evolutionary biology and iPS cells and stem cells and how they differentiate, developmental biology. Immunology, the easiest cells to manipulate at the moment are based on immune cells. And there's a lot of diseases that are propagated or maintained by deficits or imbalances in the immune system, which is sort of a catch-all term. But if you think about neuroinflammation and you think about cancer, you can think about even heart disease, where using a cell to be a regenerative therapeutic, where perhaps you can restore an organ function, or even modulate the immune system and its role in keeping that pathology going, it really becomes an incredibly powerful tool. I think one of the challenges in cell therapy, and we're kind of going to see how it evolves in the next 35 years, is what's the model going to be? How many different changes can you make to a particular cell type and still know how it's going to behave, right? You could perturb, now we're seeing cells perturbed with one gene as therapeutics. People are starting to introduce 2 genes, 3 genes, gene editing technologies where there's 1 or 2 or more gene knockouts. You can differentiate cells to go down different pathways. And so I think that there's going to be an interesting environment, both at the scientific level and also at the regulatory level, about how do you define what the cell that you're giving is? How are you going to define what the active ingredient is? It's a living drug, and that is one of its powers, in that it can sense what's going on in the host and adapt accordingly. And so how comfortable will we be with taking that risk of perhaps not knowing all of the information that we would want to know? This is potentially an area even for artificial intelligence to try to figure out, okay, if we make this many perturbations, what is the output going to be? And how can we then learn to manipulate those algorithms to try to come up with cells to do what we think they're going to do, and make sure that they stay on track, so to speak. So I think it's going to be a very interesting paradigm. I think, with not just administering the cell, but then all the things that you can add on to the cell as a delivery mechanism to have a different function. I think those are all going to be on the cusp of becoming standard realities in 35 years. But we'll see.
So what I hear you saying is actually very much thinking beyond cells as therapies, and actually even integrating a reporting function into cells. Right. So of course, in each of our disciplines, we do biomarker research, broadly construed, and a good bit of that is cells as reporters of disease state. But engineering cells to act as reporters, so you give a whatever test dose, if you will, of cells, let them traffic around the body, engage in disease tissue, come back and report back what their experience, how many made it back in the first place, yep. What their experience was. Calum, in cardiovascular disease, you guys don't biopsy disease tissue the way we do in cancer. That's, I suppose, a luxury of the cancer field. And frankly, what has been an accelerant in development has been able to really repeatedly sample tumors directly and then try to understand in blood-based biomarkers, what we can glean, what fingerprints we can see. But I've watched your work in your field evolve and feel like it's fingerprints all the time. So does this resonate for you, this idea that you could envision a more fine-tuned, high-tech way of actually engineering sensors that are circulatory?
Very much so. I think you're starting to see that emerge already. There are obviously a lot of implanted sensors in cardiology. People are looking at the left atrium as sort of real estate for sensors now. But there are also, I think, a lot of things that we recognize, work we're doing at the moment, where you can take peripheral cells and really categorize in much more detail and classify diseases based on a whole host of ex vivo or in vivo cell biology. I think there are also a lot of other, to get back to your first question even, there are a lot of other areas where you can pull out data that may actually be incredibly powerful. Everybody spends, 6-8 hours in bed. That's a remarkably valuable opportunity for sensing. Waiting in a clinic is a great opportunity for sensing. Driving in a car is a great opportunity for sensing. And much of that sensing has already been done since, 2010. Most autos in the US have had an onboard computer with a 90-minute cycle time. all of those data, all of these data are being thrown away. Could you use that as a longitudinal index of cognitive impairment? We actually found, for example, in a peripheral blood pressure monitoring study, we actually believe that the ability to Bluetooth pair your cuff with your phone is likely a better index of end organ damage than an echo or renal function. So those are the types of, I think, ambient data that we're going to have to include in the biomedical armamentarium, on top of all of the cellular data, the dedicated reporters, the implantables. I love the idea of sending in some cells to check out my coronary arteries. Those are all, I think, quite viable, and we're certainly seeing some great links in the cell biology between cardiovascular disease, both coronary disease and heart failure, and some forms of clonal hematopoiesis. I really do think there's much more connection between us than we realize. And that partly, I think, is what I was saying at the start. I really think we need to start to break down some of the barriers, the silos in medicine. I actually think individual disease-based divisions are already close to being an anachronism. We need to start to think about how we're using the tools that we all have in each of our disciplines to cross disciplines.
I think that's a great bridge back to Rudy. If I can take this kind of, unifying themes. Inflammation is definitely a unifying theme across these three disease states. And maybe in cancer, in some ways, we have the least developed understanding of pathogenic inflammation, although there's a threat of it. Maybe take that baton in terms of framing neurodegenerative disease as an inflammatory disease state, and as opposed to endpoints like destruction of normal neural tissue and plaque deposition. Back us up a step. I mean, does that resonate with where you
very
see
much.
the field evolving?
I mean, neuroinflammation at that stage of Alzheimer's disease kills at least 10 times more neurons than plaques and tangles. But it's the plaques and tangles that kill enough neurons early on to trigger the brain's very primitive innate immune system. So you have to remember, the brain's innate immune system is not much more sophisticated than that of an oyster or a horseshoe crab. It's an old system, and it's basically, you have microglial cells that are normally housekeeping and cleaning up, especially after REM during deep sleep. And if they see neurons dying, they make the same assumption they made 25,000 years ago when we were running around in the jungle and living till 25 years old. If neurons are dying, it must be encephalitis or meningitis. Wipe out the system. So now these same housekeepers are now shooting out cytokines and free radicals, and it's really deliberate friendly fire or collateral damage that's killing you're taking out the neural network. So the plaques and the tangles are killing just enough neurons and spreading of neurons dying, I call them brush fires, to trigger the immune system to say, hey, something's wrong here, take out the grid. But it's that neuroinflammation that takes out enough neurons and synapses that leads to dementia. And if you look at resilient brains, so these are people who die in the 80s and 90s, and they had no dementia, no cognitive issues. And the autopsy shows, by surprise, wow, they have enough plaques and tangles to say this is Alzheimer's. How come they didn't get it? It's always the same answer. Somehow they were spared from neuroinflammation. Their microglial cells stayed chilled out. They stayed housekeeping. So a lot of what we're thinking about now is how to come up with drugs, whether they're repurposed drugs or new compounds or natural products that can keep those microglial cells from hitting that threshold where they react with neuroinflammation. And all of us have our own threshold based on our lifestyle, how much sleep we get, diet, exercise, and our genetics. So we all have our own threshold of when we're going to trigger neuroinflammation in response to X numbers of plaques and tangles. And in the future, we'll be able to kind of modulate that number and between lifestyle and early prevention, not get to that point of neuroinflammation, because that's when the brain goes down the slippery slope.
Got it, but I hear what you're saying also with, behind it is this issue of disease course, long-term disease course, and modifying those long-term disease courses might require not just early detection, but protracted courses of treatment. I mean, I'm hypothesizing this. In cancer, we have one particular view, but I want Noubar to kind of maybe look more broadly across disease states. One issue that I've or one number that I've stared at is data exclusivity, patent protection around composition of matter, let's say, so just stick with drugs. Noubar, imagine 2054, since that's so far out, that lots of things have changed. You mentioned before the idea that like the health insurance construct dissolves a bit, and we're just in a one pool of risk and all covering each other's back in that way. Imagine the drug pricing, and this issue of data exclusivity is reframed by 35 years down the line. Is 20 years of data exclusivity, is that a rate limiter as you see it currently? I mean, is that number just a fundamental barrier to being able to develop new interventions for which we might actually need to expose a population of patients for 10 years? In cancer, we think of that as adjuvant or even prevention trials as being just beyond the pale in terms of what the current construct in terms of value creation and value capture would allow.
And you're talking about patent exclusivity, is that what you're saying? I mean, look, I'm not an expert in this area, but I would say that the time frame for drug development in the current course is such that by the time a drug is actually approved, the notion that you have that type of exclusivity and all the different ways in which it's being sliced up, I don't know that that's as effective a barrier as it was years ago, and it may be even less so in the future. If in fact it is the case that most people now work on competitors' drugs under the protection of it being for clinical research use, and that shortens the path to making much better things or other uses of things, despite the patents that have been granted. So, while we do spend a lot of time trying to figure out how to get and use patent protection, I'd say it's really less of a barrier than it might seem from the outside in the way that it's being used.
Right. So I want to entertain a couple of the comments or questions that folks in the audience have generated. So, the idea that engineering of cells is like really just made it to prime time in cancer therapeutics, leaves out manipulation technology. So I guess thinking of CRISPR as fairly recently introduced technology for potential human application. What's the game-changing potential of CRISPR technology as you see it applied to starting with cell therapy, as far as my imagination can take it?
So things like CRISPR technology allows us to take out genes of interest and also potentially correct genes of interest at specific point mutations or frame shift mutations. It really changes the scale of things that we can do with cell therapy, right? We used to just be able to introduce a new gene, not necessarily fix one, not necessarily control its expression, not have it under endogenous promoters or sort of natural control. So now with things like CRISPR-Cas9 gene editing, we can introduce genes to be controlled by specific endogenous promoters. So chimeric antigen receptors can be introduced into the natural T-cell receptor. One can fix particular mutations, like in patients who have a gene-causing mutation in FOXP3 and they don't have a regulatory T-cell environment and they get this autoimmune disease. That specific gene can be corrected using CRISPR-Cas9 editing. So I think I'm not so good with the math right up front here to tell you all exactly by how many orders of magnitude it changes, but I would say it at least, it way more than doubles or even 10x is what we can do in terms of having cells be manipulated and affect a particular disease or regenerative state that we're aiming for. It also lets us go across potentially species barriers and allogeneic barriers. So one of the barriers in using cell transplants is having to match them in some way, right? They have to be tissue type matched. Once you, and that prevents allogeneic, meaning from the same species but different people or different animals. And with CRISPR-Cas9 editing, it allows us to do allogeneic transplants without necessarily having to have long-term immunosuppressive medications. Now that experiment hasn't been formally done in human patients yet, but the possibility is out there that one can then genetically manipulate whether that allogeneic cell will be seen as foreign or not, which really also increases the capacity of using cells as off-the-shelf therapeutic agents rather than having to go back to the autologous donor and all of the complex biologistics and timelines that are involved in that process. So you could potentially have gene manipulated or gene edited cells that are sitting in a freezer, and some can become regenerative for a tissue, some can become just go in and kill cancer, which in some ways is the simplest tool, is to just have a cell kill. And so by being able to use these tissue or cell banks as therapeutic agents, I think that really also makes it much more feasible to have cells as scalable, commercializable drugs.
Okay, we have a few domains we haven't tackled, and several of the attendees are reminding me of that. So start lobbing some shots to the future in terms of 35 years out. Calum, we're not hospital administrators, so we have the luxury then of making all kinds of statements about the corrosion of how we currently construe hospitals. Pick up that thread. So, hospitals were created typically in underserved population, urban environments where people couldn't have surgery. Well, maybe nobody should have had surgery at home, but basically their homes weren't an adequate environment for them to be taken care of. So hospitals were created to be a kind of safe and hygienic environment to provide care. Okay, less of a problem, maybe no longer a problem now / 35 years from now. Do we still have hospitals as we construe them now? What's the kind of the gradient look like in terms of how people become patients and interact with healthcare?
So you can see this changing really in fairly rapid fire at the moment. We're seeing a lot of movement from hospital to the community. I think the main resistance to that actually comes more from us than from the community. I think the ability of delivery of the right information to patients to empower them to actually drive their own care is really powerful, and you're seeing that happen rapidly, not only in medicine, but actually in non-traditional industries that are beginning to take on many of the functions that we should have moved potentially to the community many, many years ago. I think hospitals will still have a very discrete function going forward. I think if you think about the transition from investigative therapy to specialty care to primary care and then to essentially systems level care, we've sort of blocked at 2 points, specialty to primary care and then primary care to systems care. And those blocks can be relieved by technology, can be relieved by information flow, they can be relieved by just the pressure of the finances of continuing to bring everything into the center. And so I think there's a real opportunity to evolve care very efficiently. I still think, as I said, there will be some central hospitals. I do think the thing I see happening is a very much more integrated set of care providers. I think the days of the largest unit in healthcare being 3 to 10 million patients, they're mitigated deeply by the need for data. We're not going to have, there's no way we can afford to be making these sort of paired agreements between two entities to share the data to ask one question at a time. That actually is, I think, an inference from everything we've heard in this conference. There are going to be 10, 12 large networks globally. We're going to stop fussing over whether it's this domain or that domain. You're going to see research be injected in every part of the system. And I think that is going to happen. It's being pulled rather than pushed. So I think that by 2054 will be very well developed. I think there are lots of commercial reasons why it will take place in the next couple of years in some very narrow spheres, and then it'll spread fairly widely.
Yeah, it's kind of taking what is currently a landscape of almost all competitive behavior and turning much of it pre-competitive.
Precisely.
All right, so Rudy, right now the sampling of real people's lives and how that transforms into disease states is, I would say, in its infancy. And if we're the ones engineering the tools, it probably is going to take even longer to get those tools in the hands of people who are developing any disease state. Neurodegenerative disease being a nice example. At least in my, what I would call lay perspective as an oncologist, people compensate and kind of, are able to cloak, even in the eyes of their family members, declining neurocognitive function. Having said that, increasingly people are interacting with devices that are interrogating their function all the time. So again, let's throw out further into the future, 35 years. How do you imagine the ability of being able to detect based on someone's like performance on puzzles on their device or whatever a technology they're interacting with, detecting declines and learning how to flag that as a population that needs to be considered as potentially having disease states.
Yeah, I mean, right now, when you go to your annual checkup, we don't check our brain, which I think will be pretty absurd.
You draw a clock, is what I remember from medical school. That's like the check on the brain.
Yeah, I mean, as Patrick Kennedy likes to say, we don't have a checkup from the neck up, except for looking into some of our sensory organs. And it's kind of absurd when you think about how important the brain is. So I think that would seem pretty silly in 35 years. But how do we do it? And we see biomarkers coming up now, things like neurofilament light chain and indicators of neuronal cell death that you can do with blood tests. I think we'll have a blood test soon for plaque and amyloid, so that you can know 15 years in advance when you should start treating without having to do imaging. But bioelectronics are making have huge momentum, and especially with the eyes. The eyes are a great window into the brain. So looking, for example, at eye movement or saccades and vestibulo-ocular response in the eyes as an indicator of brain function, as even an indicator of the amount of neuroinflammation in the brain. For example, after a concussion, that's an extreme example, you can see that there are massive problems with eye movement. That's how a neurologist checks after a player gets hit, hard hit on the field in football. So you can extrapolate that out to age, that with age, as the brain starts to go downhill and dysfunction, you see changes in the eye movement. You can do OCT, optical coherence tomography, and start seeing changes in the retina. So I think the eyes will play a huge role in the biomedical side in terms of detecting what's happening in the brain as part of your annual physical. But in terms of home monitoring, there's been advances in just speech, just hearing people in terms of finding words, finding names, speech assembly. This goes early on in many forms of dementia, aphasia, so keeping track of speech. Or in Parkinson's, keeping track of trembling in speech. So I think you'll see more of that home type of monitoring. But I would imagine that the big advance in the future, besides biomarkers, will be bioelectronics playing a key role, not just even once a year, but maybe having a device at home that's tied right into your doctor, where once a month, you're putting on certain glasses and you're sending the data in, and it's a real-time interaction with your PCP about what's happening. For children playing sports, for example, contact sports, same type of thing, keeping track of how they're doing from week to week. Did they head one too many soccer balls? So I think bioelectronics are going to play a key role for just the more routine monitoring of brain health in the future. And I think the eyes will be very important in that regard.
That was good. I like that. That feels far out to me. So, Noubar, can I ask you to take on one specific domain, which is kind of the academic investor interface. By that I mean centers where discoveries are made. It could be hospital-based centers, as each of us think about it. As I see it, having co-founded a handful of companies, there's this incubating of an idea, pitching, trying to find kind of a receptive audience, and then if there's a business model where there's a kind of tip of the spear idea, okay, launch it with the idea that hopefully there's some ideas behind that would broaden out the approach beyond a single concept. This is how I'm construing the past 20 years of what I've seen. But I've also seen some evolution in how investors think about sort of sampling the discovery space and what's ready to be translated. So it comes in two forms as I've seen it. One is private capital approaching universities and seeding incubators. In other words, sort of putting money to work, within the walls of entities that haven't yet transitioned or out-licensed technology because maybe it's not ready to go. So it's crossing the line in that way. The other is watching venture incubate ideas more before launching them. I've seen Flagship doing this, but a few other firms around town and across the country as well, as opposed to just this, light the match, start the company, more conventional concept, but that you actually kind of stew over areas of technology and potential application, and then really launch and invest once you feel like you've derived that insight. Could you give me a few thoughts, again, looking far out here, decade by decade over the next few, of what do you see the landscape looking like in terms of trying to translate science to medicine, academic to the venture community or investor community?
So I think I started being involved in starting companies in this space in 1987. That was a little after 1984,
yeah.
which is, I guess, the launching point for this. And if you go back then, the environment was a few so-called venture capitalists who would invest $1 million, $2 million, maximum $3, $4 million into companies. There was maybe a dozen things that were basically being started a year, and then 3 dozen that weren't getting funded. There will always be companies that don't get funded. There was a funding gap then. There'll be a funding gap 35 years from now. But what has changed is just the sheer scale and the level of expertise and the kind of network effect of all of this, obviously Boston being a huge beneficiary of that. But as well, as you're saying, I think the models, people are experimenting with different models. I would kind of frame it this way. I think that the way science advances and then leads to innovations, which in turn invite applications and then invite capital to try to create, deliver, and extract value out of it, is a kind of, there's this arrow of time, and that's how it mostly happens. It is interesting, since we're talking about the future, to think of it backwards and to say, instead of asking what can we do with what we've just discovered, to ask what might exist, what could exist, what should exist, and then tie it back to the present, which is increasingly the kind of innovation that we, at least at Flagship, try to practice. That's a little more than incubating ideas. That's actually looking at the present, future backwards. And the present looks pretty different in that way than if you just prosecute it present forward. For example, in the present, you can go in every which direction. If you pick a point in the future that you want to aim at and then come backwards, now you're trying to figure out, how do I get there from here? So these are things that are being experimented with. I'll say maybe this as a more general comment, and just to kind of be provocative in the morning here. In the way science is done, the kind of peer process of reviewing, like microglia, culling, pruning, kind of what it is that you're allowed to publish and what you're not, and what you're allowed to say, what you're not, is a systemic effort to enforce reasonableness. And the definition kind of that we follow is that you need to say reasonable things that extend what is known. You need to generate data that support your claims based on hypotheses, and that's great. But the notion that breakthrough advances, other than over very long periods of time, could come out of reasonable people doing reasonable things and expecting extraordinary results seems to be illogical. So it actually defies reason that the only place you would look for unreasonable breakthroughs is through this gradual collective activity. So I think it's going to take both. It's not that that's not going to produce breakthroughs. In the fullness of time, it does. I'll also tell you one other thing, having done this now for way too long. I think that the way innovation happens and the way entrepreneurs tell about it actually is always in hindsight, and it's the difference between rationale and rationalization. The reason people do things, the reason investors invest, follows some rationale. The actual story at the end turns out to be completely different, and people tell it in a way that looks completely logical, but it almost never is. If one believes that, then you wouldn't really want to follow those steps to go find major unreasonable breakthroughs. A lot of what was said on this panel would seem unreasonable to people today. That's why we think it can only happen in 35 years, because even as scientists, we're allowed to project unreasonable things as long as it's far enough out. I think the job of entrepreneurs and innovators is to actually pull that time frame and be willing to look foolish saying unreasonable things long enough that you can actually get resources to do it. So my advice to people who are trying to raise money is, don't kid yourself that the most reasonable version of what you're proposing is ever going to attract a lot of capital.
I love it. Well, that's got to be the right. Yeah, that is so the closing word. Thank you so much. I want to thank the panelists. This has really been inspiring. At least for today, it inspires me to say a bunch of unreasonable things for the remaining hours. So thank you all for your attention and for your questions as well. I think we have a break now, and then we'll be back with the next panel. Thank you.